Last lecture is endocrine disorders, and this is so endocrine, right? Y'all know what endocrine is? Y'all know the different types of signaling?
Yeah.
Endocrine is what? Yeah, it's signaling at a long distance, right? It's like across the bloodstream. This is like hormones that it's typically hormones that are released in your bloodstream that act on different organs. Do you know what paracrine is?
Yeah.
Which is what?
The paracrine, and there's autocrine.
This autocrine's the last one.
The paracrine, I guess, is.
So it's locally acting. So it's nearby cells and organs.
And autocrine is self.
Endocrine itself, yeah. So yeah, we're going to be talking about kind of overview of the endocrine system, thyroid disorders, adrenal disorders, and then diagnostic strategies for that. So here's kind of a picture of what we just talked about. The endocrine signaling is long distance, autocrine is self, and then paracrine is neighboring. So yeah, we're talking about endocrine signaling on this slide. Okay. So the ability to respond to hormones. So yeah, we're going to be talking about a lot of hormones today, and hormones respond to, our cells respond to hormones through receptors, and then the receptors typically trigger primary and secondary signaling messengers, which will then ultimately lead to transcription factor upregulation. And so whenever there are more receptors, you have more of a response. If you have less receptors, you have less of a response. And so you can regulate how hormones act at multiple different stages. The first being how much of the hormone is released. The second being how much of the receptor you have. The third being how much of the secondary messenger you have. And then the fourth being cell regulatory things about the transcription factor. We're not going to go into nearly all of that. We're mostly going to be talking about how you change hormone levels will change how much of a response there is. So specifically, we're going to be talking about a lot of. This is annoying. This is the annoying power button that's broken. Hold on. It's like it has some timer on it.
Oh, wow.
And I don't know how to delete it. Hold on. There's a timer on each slide, so it like changes the slide automatically every
At the top? Oh yeah.
What?
Slideshow. At the top in the slideshow, you know.
Oh, there it is.
And it says use timing. Uncheck it. Right there.
What is?
Oh,
this.
Okay. Oh my god. And then save it.
So we just gotta okay. Hopefully that fixes it. All right. So where are we at? Blah blah blah. Okay. So so what we're going to be talking about today are a lot of hormones, and all the hormones that we're going to be talking about today are released is regulated by this hypothalamus pituitary axis. So the general trend that we're going to see is that hormones are released from the hypothalamus, and then they are released, and then they act on the pituitary gland. The pituitary gland will sense that signaling event and then release a separate hormone that then is released into the bloodstream and then will act on downstream organs in a signaling manner.
This is our last anatomy lecture, right?
And so what? Here are a lot of great examples that work this way, right? So you have, so here you can see the hormone that's released by the hypothalamus. Over here, this is the hormone that's released by the hypothalamus. It will then bind to G protein couple receptors on the pituitary gland, the anterior pituitary gland. those G protein coupled receptors have associated G proteins. I don't know if y'all know how G protein coupled receptors work, but they're a receptor that has a protein on the cytoplasmic tail. So whatever binds the G protein coupled receptor has an associated G protein, and that gets released into the cytoplasm and then will mediate downstream signaling. So these are all the G proteins that get released, and then a signaling event will happen in the cells of the anterior pituitary that will release a second hormone that is listed on this row right here. That's like TSH, LH, FSH, those kind of things. And then that will be released from the anterior pituitary into your circulation, where they will then bind to downstream target tissues that have a lot of examples here. Things like your thyroid, adrenal cortex, etc. And so what we're going to be talking about, we're really just going to dive into two examples and the pathology associated with those two. But these are general principles that you can apply to a lot of other pathways, as long as you just learn the specifics of the rest of the pathways. Now, how these things are regulated, there are different problems that happen. So if it's a primary cause of whatever the issue is, usually the issue is the gland that's producing the hormone isn't producing that hormone, and so it's not having an effect on the target tissue itself. If there's a problem upstream of that with the anterior pituitary, and the anterior pituitary is defective, that's when you have a secondary cause, and then if it's one layer deeper, it's a tertiary cause. So make sure you understand what happens, because what occurs is that there's this negative feedback loop, that whenever the target organ is releases its hormone, it has a negative feedback loop to regulate how much of the stimulating hormone is produced. Because obviously you want, like, if your anterior pituitary, for example, is producing some hormone that's stimulating the production of another hormone, you want to have some type of regulatory loop so that it's just not producing high levels of that hormone consistently. We're going to be talking about these two examples. The first being hypothalamic pituitary thyroid axis. So this is where you have TRH being released from the hypothalamus. That's acting on the anterior pituitary. That ultimately releases TSH, which is thyroid stimulating hormone. TRH is thyrotropin releasing hormone. And when TSH is released, it acts on your thyroid, and your thyroid will produce subsequent hormones. These are thyroid hormones called T3 and T4, and those have an effect on the metabolism of your body. And so we'll talk about that right now. So T3 and T4, what these are thyroid hormones, and you can see pictures of them in the bottom right corner. I don't want y'all to memorize these structures. This isn't like an organic chemistry class. All I want y'all to get at is their names are named this way because of the number of iodines present on the chemical itself. So when you look at T4, it has 4 spots that have iodines on these conjugated planar aromatic compounds. But T3 only has 3 iodines. So that's where they get their namesake from. Regardless, what these do in concert is that, you can also look at the rest of the molecule and see that it's pretty much identical, right? The only variation between T4 and T3 is the number of iodines. So what these hormones do in and of themselves is that they increase the metabolic rate of your body. So these get released by your thyroid and then and do various things like mobilizing fats, mobilizing carbohydrates, increasing your metabolic rate. They enhance your cardiovascular and respiratory functions, which are associated with metabolism. They increase your appetite, and because you're mobilizing fats and carbohydrates that are stored, typically these can be associated with weight loss as well. So all this to say is that if you have a problem with this, there's a lot of weight issues with this. I know my sisters have like problems with their thyroid and they have a whole bunch of issues that pop up for them. So what you can do to test these things is that because T3 and T4 are made in the thyroid and they incorporate iodine, what you can do is you can do radioactive iodine in the diet, and then it'll be absorbed in the thymus, the thyroid, and then you can see how well there's an absorption of that iodine specifically in that, and you can just image that. As far as what these specifically do, T3 stimulates adipocytes to mobilize fats. So adipocytes are where your body stores fats, and they store fats as fatty acids and glycerols. But your fat cells can release fats into the bloodstream, and they can be conjugated to either if they're full on fat still, they can be conjugated to those LDLs and HDLs that we talked about in the cardiovascular lectures. But if they're fatty acids, they can be conjugated to something called albumins. All this to say is that it's mobilized because it's a hydrophobic molecule in a hydrophilic environment, and so you need to have a carrier of these things. But it'll eventually mobilize these fats, and T3 is what stimulates the adipocytes to do that. Additionally, T3 also activates transcription factors to synthesize mRNA for the epinephrine receptor. And so I think y'all can see this pretty well. So what happens is that when you have T3 and T4 being released, these work together to express the epinephrine receptor on cells. And this is important because whenever epinephrine gets made, what that results in is it's like your fight or flight molecules, right? So you need to mobilize a lot of energy, things like fats and carbohydrates. You need to mobilize them to utilize them to, either run away from the cheetah attacking you or whatever it may be. It's you're in fight or flight. Run away from the criminal in Shreveport who's trying to shoot you. Whatever you want to imagine. Dog, sure. And so the way this works is that T3 activates the transcription factor to synthesize the mRNA for the epinephrine receptor. So you can kind of see a picture of this here. So T3 gets pumped into the cells, and then it'll bind to a transcription factor. The transcription factor acts as a transcription factor, and then transcription, right, is DNA to RNA. So you make RNA that then exits the nucleus, and then it encodes for the epinephrine receptor. So the receptor for epinephrine, meaning you're going to go through translation of the epinephrine receptor, and it's going to be deposited on the surface of the cell. So whenever epinephrine gets released, you can quickly respond to that in its own signaling cascade. And I think that's a test question, actually. It's like, what does T3 do? And you have to know that it's a transcription factor, but I can't remember fully. But yeah, make sure you study this slide. I think there's a test question in there somewhere. All right, so whenever you have disorders with this whole pathway, specifically thyroid disorders, you can either lead to hypothyroidism or hyperthyroidism. So it kind of makes sense intuitively that if you don't have enough T3 and T4 being produced, what do you think is going to happen? What's going to happen is that you have that metabolism that T3 and T4 support is decreased because you just don't have those hormones there. So you have things like weight gain, peripheral edema, lethargy because you're not making that energy or you're not utilizing the energy that's there, decreased thyroid hormone action, weak muscles because, again, that's an energy thing, and then a hypometabolic state. All of that makes sense, right? This contrasts to hyperthyroidism, where it's like the flip, right? You have a lot of energy you have a lot of energetic flux through your body, And what that's going to result in is a high amount of weight loss. Your body corrects for that weight loss by trying to increase your appetite, and you have a hypermetabolic state. When you use a whole bunch of energy as well, you get things like increased amount of anxiety, restlessness, emotional instability, and you get this bulging eye. I think we have a picture of it. Yeah. Okay, we're going to be talking about these things. We have a picture of it coming up. But so what causes this, it's a lot of genetic associations and congenital it's a lot of it's a lot of genetic stuff. One of these examples is a congenital hypothyroidism, where you just have a lack of a thyroid gland or an abnormal synthesis of the thyroid hormone. But then there can also be deficiencies in the hormone that stimulates the thyroid and the TSH secretion. And there's a lot of problems with this, like mental and physical impairments if it goes untreated. There's also acquired hypothyroidism that results from the destruction or dysfunction of the thyroid gland itself. And that can be caused by surgical thyroidectomy or an ablation of the gland with radiation, anti-thyroid drugs, or iodine deficiencies. And so you can replace it with T4 hormone replacement. The reason why it's T4 is because there's a metabolic way to get that iodine off of T4 and convert it into T3. But it is harder genetically for you to convert T3 into T4. So a lot of times you can just treat with T4 and then become fine. There's also, so this is something that pops up a lot in people. It's Hashimoto thyroiditis. So thyroiditis, you can imagine, is inflammation of the thyroid. And so it's associated with the immune system. And what's happening here is that the thyroid gland is being attacked by the immune system. So it's an autoimmune disorder. And because the cells are, so what happens is you have B cells, or the mature version of B cells, or plasma cells. This picture calls them plasma cells, but they release these antibodies that attack these thyroid cells. And because these thyroid cells are dying, it releases all the cytoplasmic components of the thyroid cells, and one of them is a thyroid peroxidase. And so what will happen is your body sees this thyroid peroxidase in a place that it's not supposed to be, and you develop antibodies against that. And so a way that you can test for Hashimoto thyroiditis is that if you have anti-thyroiditis peroxidase antibodies, then this is like an indication that the thyroid gland is being destroyed at an increased rate compared to healthy people. And so that's a way that you can have hyperthyroidism. So all of these symptoms that we talked about here on the left is applicable as far as symptomology of Hashimoto's thyroiditis.
I remember Hashimoto is a Japanese guy, I think.
Yep, you got it. No, that's exactly right. That's where it gets its name from. In this slide, I think it even says, yeah, so a lot more girls get this than guys, 5-to-1 ratio. But my best friend's dad has this, and so it's like he's like one of the rare guys that has it. So I learned about this like years before I took this class.
Isn't that the expo stuff with the bulging eyes?
So that's it's Graves' disease. Which same symptom, different causes, right? Exophthalmos.
When do you get the endo one? You don't remember? When the eyes are like sinking in?
We talked about it in this class?
No, I remember this from never mind.
Okay. So Graves' disease. So this is where you had hyperthyroidism. This is an example of hyperthyroidism, and it is also an autoimmune disorder where you have abnormal stimulation of the thyroid by antibodies. So this is weird, right? So this is an antibody. Antibodies can take a whole bunch of different shapes of things, and so most of the time they're binding to pathogens or things to activate the immune system. But this is a weird situation where your antibodies that are being produced by plasma B cells are actually stimulating the receptor, and because the receptors are stimulated by antibodies rather than the hormone, you have overactive binding of these receptors. But the same signaling, but you still trigger the same signaling pathways as if the hormone were there itself. So symptoms associated with this are, so make sure you get that, because that's going to be a test question. It's like one of the options is like, I forget how it works exactly, but it's like comparing and contrasting hyper and hypo. And you have to know that the hypothyroidism one is an antibody that destroys the cells, while the hyper is the one that stimulates it. So make sure to get that clear in your heads. So a lot of symptoms associated with this: bulging eyes, heat intolerance, anxiety, high appetite, low body weight, high heart rate. And so the way that you can kind of treat this is you just got to make the thyroid less active. You can remove part of the gland, treat it with radioactive iodine, or there's certain drugs that decrease thyroid function as well. And diagnosis of the stuff, this is what I was trying to say. So you can treat patients with these iodines and then image it, and you can see like a normal integration of that iodine over a certain amount of time in the thyroid. Y'all know where the thyroid gland is? You've learned this? Yeah, it's kind of by your neck, at the base of your neck, above your heart. And so you can image the thyroid, and then if there's a ton of incorporation of that iodine, usually that's a very active thyroid gland. So if you have something like these antibodies stimulating that, if you have these antibodies that are stimulating the thyroid gland, well, the downstream signaling of the thyroid is going to be overactive, and you're going to have a lot of synthesis of these thyroid glands, and so you're going to be absorbing a lot of iodine to keep up with the synthesis of T3 and T4, and so that's why there's so much incorporation of iodine. Most of the iodine you consume, like a vast majority of it gets incorporated into the thyroid. This is like the main thing that iodine does in your body. And iodine doesn't really do a ton of other things. There's not a lot of like buffer components or cell signaling that involves this other than this T3 and T4. So it's important to get iodine in your body, right? And so this used to be a huge problem. So there's a lot of iodine in seafood, particularly. So it's not a problem in coastal areas where seafood is a regular component of people's diets. But in places like the Midwest, there is iodine deficiencies because people just aren't getting iodine, and so there's like a public health initiative to iodinize salt, and so you can still see that iodized salt that can still be sold. It's pretty much sold to everyone, but places in Louisiana mostly don't need it, and other coastal places. It's mostly for places that just don't have access to good seafood. Regardless, there's a lot of iodized salts, and that's just a way that you can incorporate the proper amount of iodine in your body. Because if you don't get enough of it, you can develop things like goiters, which you can see here. And so what's going on there is that the iodine needs to be incorporated into these molecules for a normal thyroid functioning. If not, these cells will start to swell and grow, and that's how these goiters develop over time. Swelling of the base of the neck, tight feeling in the throat. Most common cause is lack of iodine in the diet. There you go. And so that's why this initiative was initiated. All right, so that's the thyroid. We're also going to talk about adrenal disorders. So y'all know where the adrenal gland is? Where is it? Yeah, exactly. I think there's a picture of it somewhere sitting on top of a kidney. whatever. Yeah, you got it. It's on top of the kidney. So we're looking at a lot of the same signaling components as the thyroid, right? So you still have the hypothalamus secreting hormones that act on the anterior pituitary, and then that's secreting hormones that then act on the adrenal gland, in this case, instead of the thyroid. And the hormones that get secreted specifically is this ACTH. And what this is going to do, adrenal cortical function is essential for life. Adrenal insufficiency is related to mainly to glucocorticoid or mineralocorticoid deficiencies. So what the adrenal gland is going to produce is mostly cortisol and aldosterone. So ACTH is binding to the adrenal gland to produce cortisol. And so you can kind of see the signaling here. So we can see that the adrenal gland is releasing cortisol, and that cortisol is acting as a negative feedback loop for both the anterior pituitary and the hypothalamus. So this cortisol is released by the adrenal cortex in response to ACTH, and it's going to have a lot of psychological and stuff. This is the main hormone that's associated with stress and anxiety. Its highest levels fluctuate throughout the day, but it's highest in the early morning. And it has anti-inflammatory actions as well. So this is also released whenever there's injuries for anti-inflammation, but that's kind of a separate thing than what's going on with the adrenal gland. And you can test directly for cortisol levels with just by looking at the blood and urine examination for metabolic end products. But importantly, what this does is it also stimulates gluconeogenesis. Do you know what that is? Yeah, it's the synthesis of glucose from metabolic intermediates, but it's intellectually you can think about it as the reverse of glycolysis, but because it's taking things like pyruvate and converting them to glucose. Really, really important for metabolism. Insofar as whenever you don't have enough blood sugar, your body can make glucose because things like your brain can only function based off of glucose. It can't use your brain cannot use fat metabolism at all. So it needs glucose to be survived. So your liver has a way of going through gluconeogenesis, but that whole entire process is stimulated by cortisol. So all that to say is that whenever you don't have functioning cortisol releasing, right? So deficiencies in the adrenal insufficiency, it looks almost like the opposite of what's going on with the thyroid gland. That insufficiency leads to weight loss, fatigue, weakness, and it's all because of that stimulation of gluconeogenesis. And then obviously the opposite is also true, where you have adrenal excess will lead to increases in weight gain, and you get a lot of the moon face, and which is just weight gain in the face. And then there's also emotional components and emotional swings and stuff like that. You have a higher chance of diabetes with adrenal excess as well. Okay, so we have adrenal excess. A good example of adrenal excess is Cushing's syndrome. Yeah. I thought you were just looking at the next slide. That's good. Y'all have seen this to some capacity. So what's going on here is that you have elevated cortisol. And what's going on here is that other organs are producing this ACTH, which is mostly supposed to be produced by the anterior pituitary, right? So when other organs are producing it, it's these ACTH is going to just act like ACTH, regardless of its original source. But excess amounts are being released from these other organs, and you're still stimulating the adrenal gland. And so you have excess amounts of cortisol that's being produced. And so it comes from different places. There's 3 different forms: the pituitary form, the adrenal form, and the ectopic form. So this would be the ectopic form as far as where it's coming from. And so what happens is, because you have so much cortisol in your body, you have loss of diurnal fluctuations in cortisol secretions. And so you don't have the normal regular hormonal releases that are regulated tightly by the hypothalamus, which are associated with your sleeping patterns and what's that called? Your circadian rhythm. There you go. And so as you can imagine, there's just the excessive cortisol is going to also just be associated with all these adrenal excess symptoms that we see here. And there are treatments for this, which are surgical or radiation, but it depends on kind of the form where it's coming from. So you have long-term oral corticosteroids medications, such as prednisone taken from rheumatoid arthritis. So people with arthritis are getting these corticosteroids, and then repeated local injections of corticosteroids to treat joint pain. That's also ways that you can develop Cushing's syndrome independent of your actual body's producing the hormone itself. So because you're getting these treatments, you have excess amounts of. So as far as an example of adrenal insufficiency, this is Addison's disease. This is an autoimmune disorder where you have destruction of the adrenal cortex. So it's very similar to what's going on with the thyroid. And so you have the adrenal cortex hormones are drastically deficient because they're being destroyed by the immune system, and ACTH levels are elevated because there's not that negative feedback loop. It's not apparent until 90% of the adrenal cortex is really damaged, poor intolerance, and these people typically have darker skin color. So I think, what's his name? The president, John F. Kennedy. I think he had Addison's disease, or at least it's out there online that he had Addison's disease, and because he was like a kind of a darker pigment than most like typical white people. And it's kind of an interesting reason as to why. So this enzyme, or the enzymes that are associated with the metabolism of this, is found on one gene called POMC, and there's the production of the melanin stimulating hormone is produced on the same gene. So if you have overproduction of, they're like genetically linked together. This is called genetic linkage that you might have heard of. So they're genetically linked together, and so if you produce one, you produce the other, and so you have this melanin stimulating hormone that's produced in the same way. And you'll see at the same time that ACTH is produced. Yeah, I'm sure they can. But you'll probably see the pigment effects a little bit less. I don't think it's like it's not like the difference between like you know how black people can become albino, or they can be born albino, and then it's like night and day as to like what their skin is. So it's like night and day between what they look like. Like I don't think it's like those kind of differences. I think it's more like tonal.
Like Italian?
All the footage I see of him is black and white.
I'm looking at it.
What?
He looked like a normal, like,
You're looking at a picture of him? Let me see.
he was actually in my team.
Oh. He wasn't around? Yeah, I don't know. Maybe he. I don't know. I'm just saying what I read online. Did you do attic? Oh, okay. Yeah. So did he do attic?
It says he had it.
Yeah. So I don't know.
Maybe he didn't have this skin color thing, but maybe he had all the other.
Well, people. When I saw this, people online, wherever I read that from, people online said he had a darker skin color than his siblings. So maybe that's where they're getting it from. Regardless, I think those are spray tans. Yeah. Anyway, you can have lifelong replacement. So yeah, we can see here. So this is what like the gene looks like. You have the gamma melanin stimulating hormone MSH, and then ACTH is on that same one, as well as this in beta endorphin. I don't know what that's. Maybe people like that are also happier or something. I don't know. Yeah, so there you go. So last thing we're going to look at is just diagnostic strategies for these hormones. Pretty easily put. You don't have to memorize these levels, but you could just take a blood draw and look at what T4 levels are like. And so you can administer ACTH accordingly. And then as far as these disorders, you can also look at what's going on with the antibodies. There are different tests that you can look to see how many or what type of antibodies are in people's bloods. And so you can find out things like Hashimoto's disease, and you can see how reactive they are with other things. So there's just diagnostic antibody tests called ELISAs, but we won't go into that. The presence of and then also same thing for Addison's disease as well. Presence of autoantibodies against the adrenals. And then there's also genetic testing. You can look at genetic associations with these diseases and imaging methods like when you administer the iodine that we talked about. So here's a case study that I guess we'll go over briefly, and then we'll get out of here early. So if we have a 45-year-old female with fatigue, mood swing, depression, muscle weakness, oligonuria, cold intolerance, and gains weight over a period, we typically that's like we talked about two hypothyroidism, or what else is associated with so what Cushing's disease is an example of what? What's the second set that we talked about? That's not the thyroid, but the adrenal. Yeah. So hyperadrenalism, right? So what you would do is you have two options here, right? You either have you have either adrenal excess, which is associated with weight gain. Where does it say it? Increased subclavian fat, right? You have adrenal excess or hypothyroidism here. Both are associated with weight gain, right? So we have to kind of distinguish between those two. So the easy way to distinguish between those two is to take a blood draw and take a look at what's going on with the T4, right? So if you take a look at that and then you see the T4 is either normal or elevated, you can kind of compare. So I'll give you on the test, I'll give you like the proper ranges for these questions. I don't want y'all to memorize the examples here, but you can see here that normal ranges are between 5 and 11, but the total amount of T4 and the free amount of T4 is under, right? So you can see that that's probably a hypothyroidism rather than adrenal insufficiency. Does that make sense? What is the direction of the change? Yeah, so you have hypothyroidism. I don't know what this is saying. So that's pretty much what the questions are going to look like. I'm going to give you like a range of stuff with like a set of symptoms, and then you just have to identify hypo versus hyper, and if it's pituitary or adrenal. Does that make sense? So with hypothyroidism, you'd want to know what's the cause of that hypothyroidism, and is the immune system attacking that thyroid gland? And so you can look at antithyroid peroxidase antibodies and see, you can diagnose Hashimoto's or not, right? Makes sense? It's pretty intuitive. So this is another case study, and we'll just run through it. So high cortisol levels and high ACTH levels. There's a hyperfunction, and you can tell that the anterior pituitary is not working correctly. So so after you do an MRI, you can see that there's like a tumor there, pituitary tumor, and then that's associated with Cushing syndrome. So y'all can like run through that, and then you'll see on the practice test what kind of stuff the specific test questions are going to look like, at least for this stuff. But that's kind of how you run through that diagnostic strategy. Is you look at your symptoms first, you then run. I mean, this is basic like healthcare stuff. You look at your symptoms first, you then come up with some diagnostic tests that can help you narrow down between the number of options that are available to you, and then you kind of see a distinguishing test to see which diseases it might be. With that being said, we have a test next week, right? So I will get the practice test posted. The practice test is made already, I think. Yeah, I made it already. I made it a couple days ago. So the practice test is made. I'll get that posted soon, and so make sure you run to that. And then if anything pops up while y'all are studying, please just email me this weekend, and we'll get anything clarified. But yeah, it's on 8 lectures this time, so make sure to go back and study those 2 that were just posted on YouTube if you haven't looked at them already. And then I'm trying to think, is there anything else? I'll post a bonus as well for y'all to do. Y'all don't have to think about it until after y'all's exam. Just get it done by like Saturday at 11:59, meaning if you waited until Sunday, it's too late type of stuff. It's by midnight on Saturday. So take a look at that. And anything else?
I think all of us just want to die.
Yeah.